To begin with, I want us to look at enlargement. Which is that transformation that I intended to show you. Remember, in a previous tutorial, I showed you how to perform reflection and rotation. In this one, we're going to tackle enlargement and translation. So let's begin. First of all, enlargement is defined by center of enlargement and enlargement scale factor, or if you like, linear scale factor, because they're just the same. In this tutorial, let's use COE to mean center of enlargement and LSF or ESF to mean enlargement or linear scale factor. And so what we are saying here is enlargement, for it to happen, we must have a center about which enlargement is being performed. We are also saying that we must have an enlargement scale factor, which also is called linear scale factor. To begin with, let's consider two examples. And to begin with, we have this example here. We have a smaller triangle, this one here. Let's have it as our object at this point, and we have a bigger one which has been enlarged. And the enlargement scale factor in this case is positive 2. Positive 2, that means the enlarged object, which now forms the image, this bigger one here, is twice as big. It's on the same side of the enlargement scale factor as the object. So this is a simple question, where we are enlarging this small triangle here with a positive 2 linear scale factor or enlargement scale factor, and the center of enlargement in this case is the point that I have showed there. So basically, I should say, when the enlargement scale factor is a positive 2, and the object and image happen to be at the same side. Since in our case it's positive 2, the image is twice as big and also is twice as far from the center of enlargement as the object. That is important for me to say. The 2, that is number 2, means the object is twice as big and twice as far as the object from the center of enlargement. Maybe another case is where we have this second diagram here. We have this smaller figure, which is a smaller triangle, which has been enlarged, and we get this other one here. Now in this case, the enlargement scale factor is negative 2. The object and the image are on opposite sides of the center of enlargement. Again, the image is overturned version of the object. What else do we know? The image is twice as far and also twice as big. This is very similar to our previous case, although in this case the object and image are on opposite sides of the center of enlargement. Well, this is basically how enlargement happens. Whenever it's positive, the object and image are on the same side, like in this first example. Whenever it's negative, they're on opposite sides, like in this other case here. So that's important for us to consider. Maybe I should say that in both cases the object is enlarged, and of course that has been said and also shown in the diagram there. Let's consider a real actual example on the Cartesian plane. We have a triangle PQR. The coordinates are given there, and so we are told to enlarge this one here. We have two questions. The first question is, perform an enlargement of this diagram here, of this triangle, with the center of enlargement being 0, 1, and the enlargement scale factor being positive 3. Well, maybe I should mention, since the enlargement scale factor is positive, the object will be on the same side as the image. That means the image will be the same side from the center of enlargement as the object. So where the center of enlargement in our case is a 0, 1, this point where I have the laser, the red laser, I hope you can see it. That means that the object, this one here, and the image will be on the same side. What does that mean? It means the image will be farther in this direction here. We're going to see that. We have another question here. The center of enlargement is -1, -1, probably somewhere down here, and the enlargement scale factor is -2. That tells us that this object, the image will come on the opposite side, will be overturned, will be twice as big, twice as far on the opposite direction. That's important for me to mention. But let's consider the first question. Transforming the triangle PQR with the center of enlargement being 0, 1 and the enlargement scale factor being positive. What do we see? We have this image P prime, Q prime, R prime. This triangle is an image of this one here under a transformation of center of enlargement being 0, 1 and enlargement scale factor being positive 3. Now the image is 3 times bigger and also 3 times far and on the same side of the center of enlargement as the object. This where they have the laser there is the center of enlargement, and the image has gone the same direction as the object, twice as far and also thrice as far and thrice bigger. What can we see here? If you look at the point P prime and P, they are on a straight line which if you continue somehow passes through the center of enlargement. The same thing with Q prime and Q is on a straight line such that all of them meet at the center of enlargement. Again, also R prime and R, if you continue those ones, they meet at that point there, the same point, which is the center of enlargement. That tells us something. Whenever we have performed an enlargement of some kind, if we join 2 corresponding points and continue the lines, all the lines meet at the center of enlargement. All the lines meet at the center of enlargement. And I think you can make other inferences, but whatever inference you get there, please understand that it's supposed to help you know how to cross-check your work. Whenever you've performed an enlargement, how should the image look in relation to the object? Now, what is the relationship between the areas of the 2 triangles? Let's try and figure out the area of PQR. PQR is, you see, this height here is 3 units, and the base here is like 2 units. So if you use half base times height, the area of this is 1 over 2 times 2 times 3, which is just 3. So the area is 3 square units. What about P prime, Q prime, R prime? The distance from this point here to the point Q prime to R prime is the distance there is, you can have 9 minus 3, which is 6 units. Again, P prime to Q prime should be 13 minus 4, which is 9. So we have 9 times 6 times a half. That's a half base times height. The answer will be a half of 6, which is 3 times 9, which is 27. So the area of this one here is 27. The area of the other one is 3. The question is, how do those ones relate? Look here. Area scale factor, that's the relationship of the areas of P prime, Q prime, R prime, and PQR, is equal to the area of the bigger, that's the image, divided by area of the object, which is 27 divided by 3, and the answer is 9. Something you should notice is that 9 is actually 3 squared. And what was 3? 3 was the enlargement scale factor, or if you like, linear scale factor. So that gives us a general rule. Area scale factor is always linear scale factor squared. Area scale factor, in all cases, whenever we have performed enlargement, area scale factor can always be gotten by squaring the linear scale factor. I hope you consider that in the future. So that's it there. Linear scale factor squared always gives us area scale factor. And of course, if you're given the linear scale factor, you can always get the area scale factor. I guess there are questions that test that kind of thing. Let's consider the next example where the center of enlargement was -1, and enlargement scale factor was -2. This is the figure we get. The triangle originally was this one here. I've ensured that the diagram is a lot smaller so that you can accommodate the space that you have. So PQR is as it was at the beginning. The center of enlargement is -1, -1, where all the lines meet, and the enlargement scale factor is -2. The fact that it's negative means the object goes to the opposite side of the center of enlargement. The fact that it's 2 units, it means that the triangle P prime, Q prime, R prime is twice as big as PQR, and also twice as far. If you take the point, say, P, from the point P to the center of enlargement, this distance is a half of from here to the point P prime. That means P prime is twice as far as P from the center of enlargement. Also Q prime, this one here, is twice as far from the center of enlargement as Q, and also R prime is twice as far from the center of enlargement as R. That is important to know. Now, it's always good to notice that whether positive or negative enlargements, a point and its corresponding point on the image always lie on a straight line, such that if you continue all lines, P to P prime, Q to Q prime, R to R prime, all of them, they are on a straight line and they intersect or they meet at the center of enlargement. It's important for me to mention that. So I had said that the image is twice as far and twice bigger. That's what this statement here says, and I'd leave you to answer that. What's the area scale factor? What's the area scale factor? If you refer to the previous question, that's Roman 1 of this, the enlargement scale factor squared gave us a linear scale factor. So what do you think would be the area scale factor? You can figure that out in your own. I have another question then. What about the relationship of volumes? The relationship of volumes of similar objects. Well, this is a two-dimensional thing, so we don't have any volume here. But what about if we stretched our imagination? What would be the relationship of volumes of similar figures? Say similar pyramids or similar cubes or whatever it is, 3D figures. What would be the relationship? A general rule that is developed from the same way I developed the area scale factor is volume scale factor normally equals to linear scale factor cubed, and that also equals to the volume of the image divided the volume of the object. Well, I understand we don't have a volume here since these are two-dimensional, but allow me to use this as we stretch our imagination or application in cases where we have similar objects. If you have two similar objects, the volume scale factor can be gotten by volume of the image divided by volume of the object, and of course that answer there will be linear scale factor cubed. If we had two cubes, one is an enlargement of the other. If you get the length of the bigger one divided by the area, the length, a corresponding length in the smaller one, that will give you the linear scale factor. So the cube of that would give us the volume scale factor, and that's a general rule used elsewhere also, used everywhere in mathematics, and you can always consider that. Well, let's move on to the next transformation, and in this case we go to translation. Now, translation is largely a concept in vectors, so that's why I put that there. Now, translation is defined by a translation vector. That is important for us to notice. Translation is defined by a translation vector, or is represented with the letter T, like seen. And let's consider an example before we go to an actual question. We have a triangle A, and you're told to translate it through the vector 5, 3. What does it mean? We are told to translate the triangle A through translation vector 5, 3. What does that mean? Before we perform, I can mention this. What we are doing here is that we are moving this triangle 5 steps along the x-axis followed by 3 steps along the y-axis. That means this 5 means steps along the x-axis, the 3 means steps along the y-axis, that we move or we translate. Translate means to move an object through a given vector. In our case, 5 steps along the x-axis, 3 steps along the y-axis. How does it go? We move 5 steps, so I already have 1 here. So 2, 3, 4, 5, followed by 1, 2, 3, 4, sorry, 3. So we have moved 5 steps along the x-axis and 3 steps along the y-axis, and the triangle comes there. So this was triangle A, this is triangle A prime. Now, what else do we notice? The point, this point here of the triangle moves that way along, say, a right angle triangle of 5 by 3. The same thing to every other point moves the same distance along the same vector 5, 3. 5 steps along the x-axis, 3 steps along the y-axis. I hope that's clear. That's basically what happens in every case when we're doing translation. Now, let's consider an actual question. We have a triangle ABC, which is the coordinates given there. And the question is, translate the triangle ABC through a translation vector of 3, 4. What does that mean? It means that we'll move every part of triangle ABC 3 steps along the x-axis and 4 steps along the y-axis, and strictly that way. 3 steps along the x-axis, 4 steps along the y-axis. Strictly that way and in that order. We don't start with y, we start with x. And there you have it. The triangle ABC moves to A prime, B prime, C prime. And if you look at it, every part, say part A, the point A, sorry, moves 3 steps along the x-axis, followed by 4 steps along the y-axis. 3 steps from 2 to 5, and then 4 steps along the y-axis from the point 4 upwards up to the point we have 8. That's the same thing for B and C. Every part moves 3 steps along the x-axis and 4 steps along the y-axis. It's important for me to insist that. Now, if you get the point A and just add the translation vector, you got A prime, which is the 0.58. What do I mean? If you get 2, 4, you add 3, 4, that gives you 5, 8. That's a general rule. That means even point B and point C can be gotten without necessarily drawing even point A. You just need to have the coordinates of the point A, B, C, or whichever point you have, and add the translation vector, and that gives you the point or the image that we should get. So 2, 4, which were the coordinates of the point A, added 3, 4, which is translation vector, gives us 5, 8, which is the image of the point A. That is A prime. The same case applies to B. So you get B plus the translation vector T gives you B prime. Same thing for C. C plus T gets you C prime. And that's basically what happened. What else should we know? The lines through which every point is translated happen to be parallel lines and equal lines. That is, they are same lengths, all of them. That means A prime, B prime, and C prime are all of them the same length. They are all parallel. They all move the same distance, and that's important to notice. What else should I say? The triangle A prime, B prime, C prime is the same size as ABC. They're the same sizes, and basically that's the point there. Every point of the object moves the same distance and in opposite sense. And in an opposite sense, every point of the object moves in the same distance. I'm not sure that I should have said this. What I intended to say in this statement here is that every point, say point A, B, and C, all of them move the same distance, and that's the case there. I think they are all of them parallel. I think I wanted to mention parallel here, not opposite. So that's the case there for translation. Well, there you have it. We have transformations now. We have enlargement. We have translation. Earlier on, we had reflection and rotation. I hope you find that helpful. That's all I had for you for transformations. And as always, you can always like, subscribe, and share. And thanks for watching. And thanks anyway.